The title of this presentation is Operator Formalism for Discretely Holomorphic Parafermions of the Ashkin-Teller and Loop O of one models. To begin with a presentation overview, we'll be introducing parafermions, discrete holomorphicity, and the Cauchy-Riemann equations. And to make ourselves familiar with these types of topics and how they fit together within complex analysis and probability, we're going to introduce several works in the statistical physics / probability literature from Domino-Capon, Angler, Katola, Zahabi, Wu, Kunz, Tanhaya, Hari, and Rouhani relating to the following topics. We can look at the connections between the parafermionic observables for the Abelian, Sam-Powell, Ashkin-Teller, and the Ising models, which relates to a definition of the Cauchy-Riemann equations, which relate also to Morera's theorem, which these parafermionic observables satisfy, which can be related to the critical behavior of these models. And there are also several other topics and components of the argument that I'll provide some general overview and refer to and allude to, in which relate to irreducible representations, the Virasoro algebra, Lie algebras, divergence of the correlation length and disorder parameters. And this can also be related to properties of the staggered and odd vertex models. So in this overview slide, I'm providing many different types of terminologies across several different types of models of statistical mechanics, like 5 or 6 models, so that we can see, despite there being some difference in how properties satisfy critical or supercritical or subcritical behaviors, how there can be some similarities between these models, despite different ways that the models are defined from the probability measure that we can look at and study through disorder variables and parafermionic observables. And specifically, we're going to be drawing more of our attention to discussing how holomorphic parafermions for the Ashkin-Teller and Loop O of one models relate to each other, which share connections with the holomorphic parafermions for the Ising model. And our main reference for discussing holomorphic parafermions for the Ising model will be the paper from Angler, Katola, and Zahabi, which is a 2012 paper, which we're looking to extend of and make future use of their framework in light of a question that Domino-Capon had raised as a direction of interest from one of his papers, in which he looked at the divergence of the correlation length for the random cluster model, in which he mentioned that it would be of interest to look at what information can be extracted for parafermionic observables for other types of models rather than the random cluster model or some other types of models, under the assumption that the parafermionic observables for these models exist, and looking at how one can state several different types of properties that these models would satisfy, and how it would be possible to relate multiple models to each other at the same time. So we're first going to be describing the random cluster model, because this is the model that Domino-Capon looks at in his paper for establishing that there's a divergence of the correlation length for a range of parameters in the cluster model, for which the model undergoes a continuous phase transition. So the probability measure for the random cluster model is given by phi, and under boundary condition C, with parameters p, q at an underlying graph G, the probability of sampling a configuration omega under these boundary conditions is given by the probability to the number of open edges times 1 minus the probability to the number of closed edges times q to the number of clusters of the random cluster configuration omega, normalized by the partition function of the random cluster model, so that this expression is a probability measure. And the parafermionic observable or disorder operator that can be defined for the random cluster model is the following object. It's a discretely holomorphic function. And the way that we define and introduce this function is important, because this is going to be related to the discrete holomorphicity and the statement of the Cauchy-Riemann equations, which this function is going to satisfy. So we're looking at f of e, where e is an edge of the underlying graph that we're using to define the random cluster model over. And the parafermionic observable is given by the image under the push forward, or the image under the random cluster probability measure of the exponential of some imaginary prefactor I over 2 times the winding of some path gamma between the edges E and E of B. So E is just any edge that the path gamma traverses and E of B is the final edge that the path will traverse, times an indicator that each one of these little e's, which is each one of the edges that we look at the winding over for the parafermionic observable, belongs to the path. So from this definition of the parafermionic observable for the random cluster model, to further highlight and discuss some of the properties that this parafermionic observable can be used for in the random cluster model from previous work, relates to a result from Dumino-Kopan, in which he established the divergence of the correlation length for the random cluster model. And again, we just mentioned and make clear that the number of clusters, or the cluster parameter Q, that in the random cluster model is restricted to be between 1 and less than or equal to 4, so that the model undergoes a continuous phase transition. And this is given by the fact that the correlation length diverges, which is equivalent to saying that the reciprocal of the correlation length, which can be expressed as the minus infimum for n greater than 0 of 1 over n times the log of the random cluster probability measure taken under free boundary conditions of the probability that 0 is connected to some segment n0 approaches 0. So this is important because it demonstrates one potential use of the parafermionic observable for being able to demonstrate that the correlation length of a model can diverge, which is one way to quantify disorder and how the correlation length and other types of properties would change for models in statistical mechanics when we vary other parameters and look at the critical regime or the subcritical regime or the supercritical regime. But we can also introduce a parafermionic observable for the Ising model, which is related to the operator formalism. And we're not going to define the Ising model because everyone always defines it. And it's a very well celebrated and intensely studied model in the field. But the parafermionic observable has received less attention, but it's still a really interesting object in its own right, because it'll make use of and demonstrate how we can apply the operator formalism to study discretely holomorphic parafermions from the Ising model to also the Ashkin-Teller model when the model has two colors, as well as to the loop O of one model, which is a degeneration of the loop O of n model in the high temperature phase. So the parafermionic observable for the Ising model is given by the summation, which is normalized in the partition function of the Ising model, and it shares a commonality with the parafermionic observable for the random cluster model because it also has a winding term, which is the same imaginary per factor times some winding factor, but it also has another factor which is dependent upon the inverse temperature of the Ising model, as well as the number of edges or the cardinality of edges that belong to the path. So this is just a very similar way to define the parafermionic observable for the Ising model, which we can use and discuss and make use of for different purposes rather than the random cluster parafermionic observable, which was used to demonstrate from Dumino-Kopan's result that the correlation length diverges. But for all parafermionic observables of the Ising model, the random cluster model, the Ashkin-Teller, and the loop O of one model alike, they satisfy a discrete holomorphicity relation, which is relating to the Cauchy-Riemann equations and the Morera's theorem. And it's important that we introduce this property first, because we can look at ways to strengthen the Cauchy-Riemann equations to obtain S holomorphic, which stands for spin holomorphicity or S holomorphic equations, which can either be massive or massless, depending upon the critical temperature that we look at for the Ising model. So the general relation is that when we want to say that a holomorphic or discretely holomorphic function satisfies the Cauchy-Riemann equation, it's an equivalent condition to say that the function evaluated at Zij, namely any edge in the square lattice between the vertices I and j times the difference or the increment Zi minus Gj, vanishes. So this is very important for us because we're going to be looking at several different specific instances of this general formula when we're discussing massive and massless S holomorphicity for the Ising model and describing how these notions for massive and massless S holomorphicity can also carry over to the Ashkin-Teller model and to the loop model through some connections and observations that we'll be introducing in some later slides. And besides the parafermionic observables that we've been introducing for the random cluster for the Ising model, there's also a parafermionic observable for the Loop O of M model. And this is related to the result of Dumino-Kappan and Stas-Smirnov for establishing that the connective constant of the honeycomb lattice is square root of 2 plus square root of 2. So the parafermionic observable for the Loop O of M model, which is instead in contrast to the fact that the parafermionic observable for the random cluster and Ising model are defined over the square lattice. This parafermionic observable is defined over the hexagonal lattice, and it takes as parameters some sigma term, which we're not going to define like specifically what sigma is, because it can be kind of technical what the right definition and parameter of sigma is to take in terms of the number of loops n, which is another parameter that's introduced into the Loop O of M model. So just realize that there are some expressions involving arc cosines and I think arc sine, but I'm pretty sure I remember arc cosine, which is dependent upon the sigma parameter. But there's also other parameters, namely a and z, which are the beginning and ending points of the path that we're looking to incorporate or quantify the winding of in the parafermionic observable, as well as some other parameter x, which is just any position within the finite volume of the hexagonal lattice. And in this case, the parafermionic observable for the Loop O of M model is given by a summation over paths beginning from A to Z, which were these 2 points that we listed, that we had just mentioned, were the beginning and ending points of the path. And also under the condition that the path belongs to the finite volume, which is the exponential of minus I sigma. So another imaginary prefactor where instead the sigma parameter depends upon the number of loops and of whatever configuration for the critical point of the Loop O of M model, which we're going to introduce, which multiplies the winding number of the path. But instead, we have another factor, which is x to the number of loops of gamma. So we incorporate the number of loops in the parameter that we raise x to. So now that we've defined a couple other parafermionic observables, we'll want to introduce the last parafermionic observable that we'll be introducing and that we'll be discussing in the presentation. And then we're also going to be looking at how we can make connections from the operator formalism from Ongler, Katola, and Zahabi in the 2012 paper. So the Ashkin-Teller model is obtained from a probability measure that is proportional to coupling two Potts models together. So it's given by this Hamiltonian, which consists of two 2-point interactions and one 4-point interaction, where the 4-point interaction has a coupling constant 2, u, and the two 2-point interactions have a coupling constant of j. And the parafermionic observable for the Ashkin-Teller model is given by this function psi of r, which is given by an exponential of minus I sigma m times the winding term, which instead we express as theta. So it's given by the point r at which the path begins, as well as the winding is taken with the displacement vector from any other path, points in the path that the path traverses, as well as a spin operator, which is dependent upon r, and a disorder operator mu of m, which is also dependent on r. And the Loop O of M model, as we had introduced earlier, has its own parafermionic observable, but it's important to distinguish that between the parafermionic observable for the loop model and the parafermionic observable for the Ashkin-Teller model, that it can be dependent, that the one for the loop model is dependent upon some parameter n, which is taken strictly between 0 and 2. And this critical point was conjectured by Nienhuis to exist. And it just separates different types of subcritical and supercritical behaviors of the Loop O of M model pertaining to how large the loops are in some finite volume. And the probability measure for the loop model is given by under boundary condition C, which is supported over some finite volume of the hexagonal lattice, given by x to the number of edges of the configuration and to the number of loops of the configuration, which is normalized in the partition function of the loop model, so that we have a probability measure. And now we can actually get to describing and providing more detail on the massive and massless S holomorphicity definitions that we had mentioned hold for the Ising model, and how and in what regard these can transfer over and make use of these notions for the two-color Ashkin-Teller model and the Loop O of M models. So we'll first begin with the massive S holomorphicity for the Ising model below the critical temperature. And we have notions of massive and massless S holomorphicity, because below the critical temperature, we have a massive term which approaches 1 and degenerates to 1 as we approach the critical temperature of the Ising model, which is a half log of 1 plus square root of 2. So now we'll just provide we'll provide some discussion for the massive S holomorphicity below the critical temperature of the Ising model, and juxtapose this to the massless S holomorphicity of the Ising model at the critical temperature from the difference of this one parameter going to 1 that I just mentioned. So what we need to do is that we need to fix some inverse temperature of the Ising model, which is strictly positive, and for some inverse temperature that's strictly less than the critical temperature of the Ising model, we can introduce some complex parameters nu, which is given by the complex conjugate of this parameter lambda cubed multiplied by alpha plus I over alpha minus I, with alpha being the exponential minus 2 times the inverse temperature, as well as lambda being the exponential of I pi over 4, from which we say that a function big F, which is defined over some finite subregion of the square lattice into the complex numbers, is said to be massive S holomorphic if it satisfies these 4 equations for any face of the square lattice which has edges east, north, south, and west. So it's important to recognize that, or to realize that, these 4 equations, which are given in the definition of the massive S holomorphicity below the critical temperature for the Ising model, they exactly coincide with the Cauchy-Riemann equations that we have been introducing a general case of and a general definition of in a previous slide, with the exception that we evaluate this big function F, which is the parafermionic observable of the Ising model at n, which is the northwest face of any edge, and we relate this to the value of the parafermionic observable on the east edge. But in the second equation, we also relate the value of the parafermionic observable on the north component to the west component. And then in the third and fourth equations, we relate the value of the parafermionic observable in the S component, or the S face of the square lattice, to the east face, and also between the S face of the square lattice to the west face. So this is just a way to take the north and the south faces that are tangent or incident to any vertex of the square lattice, and to form a discrete relation between the other edges that are given from the face of the other faces which are given which lie to next to or incident to other edges of the square lattice. But the important part is that we can also take the complex conjugate of the parafermionic observable, which is multiplied by some parameter nu inverse lambda, but this nu inverse lambda appears only on the left-hand side for the first 2 Cauchy-Riemann equations that are given from this discrete holomorphic system. But in the other 2 equations, it's given by nu lambda cubed and nu inverse lambda to the minus 3. But these other parameters, nu and lambda inverse, or nu and lambda cubed, or nu and lambda minus 1 and lambda to the minus 3, they appear in the other terms of the Cauchy-Riemann equations, which are given on the right-hand side. So this is just to demonstrate how one can fix certain parameters which are given for the Ising model relating to the temperature. And below the critical temperature, there's an existence of some function which is related to the parafermionic observable, because it satisfies the Cauchy-Riemann equations. But the thing is that we have to be careful is that when we take the complex conjugate of this holomorphic function, the function from omega into the complex plane, or into the complex numbers, we have to be careful, because we have to account for some other parameters, either relating to the exponential I pi over 4, which is relating to some possible winding of the path within the collection of north, east, south, and west faces, as well as some other lambda parameter and an alpha parameter, which is related to the exponential, which is proportional to the exponential of the minus inverse temperature. But there's also a notion of massless S holomorphicity for the Ising model below the critical, or at the critical temperature. So now we're going to juxtapose, as we have been alluding to, this result to the behavior of S holomorphicity, which again we had said was standing for spin or strong holomorphicity, which is a strengthening of the Cauchy-Riemann equations, because at the critical temperature of the Ising model, we can introduce the same quantities and parameters, but the only difference is that the new parameter that we had indicated appears in the definition of the massive S holomorphic equations that we defined in the previous slide. It degenerates to 1. So wherever the new parameter was appearing, as we can see from the other terms of the Cauchy-Riemann equations, it approaches 1 for the same faces of the square lattice that we have been describing earlier, namely the north face, the east face, the west face, the south, and the south face. But we also have to look at how we can introduce a propagation mechanism for the Ising model, which is relating to how we can extend S holomorphicity or strong holomorphicity from one face of the domain or one collection of faces of the domain to the entire finite volume. So this is given by another reference from the paper, from the 2012 paper due to Angler, Katola, and Zahabi, in which they introduce us to the propagation mechanism, which is saying that for some inverse temperature, which is below the critical temperature for the Ising model, if we have an interval, which is a dual interval of a plus a half, a plus 3/2, all up to b minus a half, which is a dual interval I star to I, which is given by a to a comma a plus I all the way up to b. The S holomorphic propagator is defined from the real numbers of the dual raised to the dual interval into itself in terms of the following relation. So we introduced the propagation mechanism for the parafermionic observable at some value k, where k is some parameter or some point that lies within the bulk of the finite volume, in comparison to the left-hand point and the right-hand point. So this is given by another set of relations, which allows us to extend the strong holomorphicity to the entire volume if we just only have the notions of massive and massless S holomorphicity from one face that we've been defining in the previous two slides from the Cauchy-Riemann equations. And this is just given by a different type of expression because it's a superposition of the values of the parafermionic observable that's acted on by the propagator for the Ising model, in which if we look at the value of the image of the propagator that's acting on a function only at some point k, it's equivalent to, well, it's proportional to evaluations of the function at the point k minus 1, k plus 1, as well as the complex conjugate of each one of these three function evaluations. And there are similar expressions for the value of the propagator at the left endpoint and the value of the propagator at the right endpoint of the finite volume. And at the critical temperature of the Ising model, there's a different type of mechanism for propagation, in which this notion of propagation at the critical temperature is especially important for us because it allows us to make different types of connections between the two-color Ashkin-Teller model and the Loop O of N model, because as we're going to be describing in a couple of slides, there's a way to couple the Loop O of N model in the high temperature phase to the Ising model, which in which the probability measure under the high temperature phase can degenerate to the O of 1 measure. But there's also a way to make a connection between this propagation mechanism of the Ising model and the propagation mechanism for the two-color Ashkin-Teller model, because we're coupling two Potts models together, and where there can be a way to couple the way that the propagation mechanism and to interpret how this propagation mechanism acts for discretely holomorphic parafermions of the Ashkin-Teller model. So in the case for the critical temperature at the Ising model, the propagation mechanism takes a little bit of a different form, but it still shares the commonality from the propagation mechanism below the critical temperature that we had introduced in the previous slide, because it's related to evaluating the value of the parafermionic observable for the Ising model at the points k, k sub l, and k sub r, which were the points that we had talked about earlier. But the difference is that there are some prefactors which appear in front of different terms that we're listing that the propagator can be expressed in terms of, namely fk minus 1, fk plus 1, and the complex conjugate of these three function evaluations, which is proportional to these duality parameters, which can be obtained from the Ising model. So there's a way to obtain dual parameters from the Ising model, which I stated in the paper, but it's just either relating to taking the hyperbolic sine of 2 times the inverse temperature or the hyperbolic cosine of 2 times the inverse temperature. And there's a similar type of duality relation that's a little bit different for the Ashkin-Teller model, which allows us to form different types, or a different propagation mechanism, but nevertheless still a propagation mechanism that has a very similar orientation and a very similar purpose of being able to extend S holomorphicity throughout the entire domain if one knows that a massive or massless S holomorphicity holds at just one face of the square lattice. But we also have to specify boundary conditions, because when we define the Cauchy-Riemann equations, we have to specify what the value of the parafermionic observable is at the boundary of the finite volume, so that we can study the behavior of this observable within the bulk of the finite volume, or the interior of the finite volume. So we say that this function little f from omega into the complex numbers is said to satisfy the Riemann boundary conditions if for any edge the value of the function evaluated at f of z is parallel to 1 over the reciprocal of tau clockwise of z, namely that f of z is a multiple of this quantity tau clockwise of z, in which this function tau of z takes the value either plus or minus 1 if the edge is vertical, or plus or minus I if the edge is horizontal. So this is just demonstrating to us how we can also encode and make use of boundary conditions for the Riemann boundary conditions for massive and massless S holomorphicity from the Cauchy-Riemann equations in the Ising model. But we also have the transfer matrix for the Ising model, which again is a different type of notion, which is satisfied in terms of some generator relations that one can formulate for the Ising model from the 2012 paper that we've been discussing. And this is really helpful for us also because we can form different types of notions for the transfer matrix from the Ising model, for the transfer matrix for the Ashkin-Teller model, and then for the loop model, there's a different type of construction for the transfer matrix that we're going to introduce due to Blot and Nienhaus. But for the Ising model, the transfer matrix takes this form, where the two generators that we're raising to the half power and the left hand and the right hand side, they're related to the exponential of this Hamiltonian of the Ising model, as well as the middle term, which is the V of V term, is an exponential of beta over 2 times another term that's very reminiscent of the Hamiltonian, because we're taking the pairwise, the closest neighbor, nearest neighbor pairwise interactions from the spin sigma I and sigma I plus 1. But we can return to the loop model because, as we have been mentioning, there's a connection between the loop model and the Ising model, in which the loop model in the high temperature phase can be coupled to a probability measure that takes this form. So we have n to the number of connected components, x to the number of edges, times an exponential of a function which is dependent upon two external fields, h and h prime. And R of sigma and R of sigma prime are respectively given by the summation over all edges of the configuration over the hexagonal lattice, as well as the number of monochromatically colored triangles. And we take this high temperature partition function to normalize this expression with, so that we have a probability measure. And under the choice of parameters, in which the inverse temperature for the Ising model can be taken as 1/2 of the absolute value of log x, and taking the n parameter to be 1 and the h prime parameter, which is setting one of the external fields to be equivalently 0, we can obtain an expression and a coupling between the Ising model and the O of 1 measure. So this is just explicitly demonstrating how we can set the loop O of n model in the high temperature phase under a certain restriction of the parameters to the O of 1 measure, which is relating to the Ising model, which can further help us interpret and make sense of the Ising model transfer matrix, the Ashkin-Teller transfer matrix, and the notions of massive and massless holomorphicity, which relate to the strengthening of the Cauchy-Riemann equations that we have been mentioning a couple of times. And this is just to provide a definition or a brief overview of the transfer matrix of the Ashkin-Teller model from the transfer matrix of the Ising model, in which the Ashkin-Teller transfer matrix has a conjugation action, much like the Ising model transfer matrix has a conjugation action. And we take these generators pk of A of t and qk of A of t, which just represent different type of generators that we can introduce for the Ashkin-Teller model from the Hamiltonian that we introduce for coupling the two Potts models together in an earlier slide, and they can satisfy some properties. I won't go through all of the exact properties, but they just relate to either some type of anti-commutativity properties, which is relating to some type of Heisenberg uncertainty principle, because some of these arguments are making use of quantum mechanics and quantum physics, which relates to the fact that we can't have infinite precision of the position of momentum of particles at the same time. And it's also relating to the duality relation that's given for the Ashkin-Teller model, which I didn't define in these slides, but it's very much related to the duality relation that one can use for the Ising model in terms of the hyperbolic sine function and the hyperbolic cosine function of the inverse temperature, or of the inverse temperature. And the transfer matrix for the loop model, just to give you an overview from the construction due to Blot and Nienhaus, is given by taking a high temperature expansion of the partition function as a sum over configurations, which is proportional to some k to the epsilon parameter and to the L parameter, and k and n are just both taken to be strictly positive, and epsilon can be some parameter, which can lead to an expression which Blot and Nienhaus obtain for the partition function in terms of this summation, which is proportional to and related to a Kronecker delta function, the number of edges and the number of loops of the loop configuration over the hexagonal lattice. And the discrete holomorphicity for many of the models that we have discussed also carries over to the lattice fermion operator for the loop model. And the lattice fermion operator is related to and used in defined in terms of some other assumptions that are introduced on the parafermionic observable. And this is helpful for us because it also demonstrates how we can further carry over and make use of the massive S holomorphicity for the loop parafermions for massive S holomorphicity for the loop parafermionic observable, in which one can have a system of four equations given the fact that the hexagonal lattice is dual to the triangular lattice that we use to define the loop O of n model. And we can obtain similar type of expressions that we had given before, namely, we evaluate the parafermionic observable on one edge, we add some complex per factor and take the complex conjugate of the parafermionic observable on the same edge. And from this massive or massless S holomorphicity, which is related to the discrete holomorphicity in the Cauchy-Riemann equations, we can obtain the value of the parafermionic observable for the loop, or the value, of the lattice fermion operator at another edge, or at another edge of the hexagonal lattice Z2, plus a complex per factor times the complex conjugate. And very similar relations hold for the remaining three equations which are given, which constitute the discrete holomorphicity relation for the lattice fermion operator, and how it directly carries over from the discrete holomorphicity relation for the parafermionic observable for the Ising model, for the Ashkin-Teller model, for the loop O of one model, the loop O of n model, and even how it can be carried over to the 8 vertex, the odd 8 vertex, the staggered 8 vertex, and the Abelian-Sampow. So conclusions is that we introduced parafermions, discrete holomorphicity in the Cauchy-Riemann equations, and we introduced several models, namely these models, the Ising and Potts models, the Ashkin-Teller model, the loop O(n) model, and the high temperature expansion of the loop O(n) model, which we looked at under a certain range of parameters to degenerate to the O of one model, so that we can form a connection and a coupling between the O of one model and the Ising model. And as discussed in the archive posting that I recently made on this topic, which I'm going to include in the link in the bio, this framework for the operator formalism can carry over to staggered 8 vertex, odd 8 vertex, and the Abelian-Sampows. And the odd 8 vertex and the staggered 8 vertex, they relate to the 6 vertex model, and that we have 2 extra configurations from the fact that we don't have to enforce the ice rule. So it's just relating to another type of model. and how one can formulate and further carry over this notion of the parafermionic observable. And thanks for watching.